Okay, good morning to everyone. I'm on the West Coast at the moment, so you're just coming up to lunch and I'm just coming up to breakfast after this. So I won't beat about the bush. I'll get on with this. Okay, let's see, as long as I can make the, oh gosh. Okay, here we go. So what I want to talk about is basically a surprising connection between some results in bifurcation theory and problems in theoretical computer science related to machine learning. I should say that everything I'm going to talk about is joint work with my collaborator, Yossi Arjabani, who's a theoretical computer scientist. So let me say, oh, why isn't this going forward? Oh. There we go. Okay, this talk is a little tricky to give because the results from bifurcation theory I'm going to talk about, although they're in a way quite old, are probably unfamiliar to the audience. And similarly for the methods, which depend on some fairly difficult stuff in non-trivial analytic geometry, analysis, representation theory. So I don't really want to get into the technical side at all in this talk. I just kind of want to give you an idea of what's going on. At the moment, I can't get this thing to update the slides. That's ridiculous. Does anyone know what the command is for? I mean, I'm trying to move forward on the slides here. It won't move forward. Trouble with Apple. It's an Apple machine.
Click on the application you're using. Yeah. And then try to use your arrow. Yeah. Just so
I'm trying to. I'm using just Adobe Acrobat. Let me
close your find. Yeah. Okay. That's it.
Let's go back to that.
Yeah.
Okay. Let's try again. Oh, that's the problem, is it?
Yeah, close that. Yeah, close that.
Oh, I've had endless trouble with this.
And then,
okay,
and
right.
Then turn on your yeah.
Okay, appreciate that. Okay, it's hard enough giving a talk on Zoom, let alone if one's having this sort of problem. Yes, so let me say that the talk is tricky in a way to give because of the results from bifurcation theory, as I said. So how to proceed on all this? It's still not working. Okay, so let's, you all want to get to London, I'm sure. So let me...
Yeah, so maybe minimize, I mean, don't use full screens.
Yeah, I'm going to do that. Yeah, that's obviously the best thing to do. So let me shift this around a bit to get a bit more space. Okay, again, my apologies for this. Okay, so let's try again.
What if you click on the arrows? Yeah, okay, yeah, all right. Okay.
Yeah, well, I'm using the arrows. That's what I'm using.
Yeah.
Okay, so how to proceed in the talk? What I'm going to do is to assume a little familiarity with dynamical systems and say very little about the theoretical computer science. Though what I say will be said in the next minute or two. I can always scroll down, I suppose. It's ridiculous. I don't know why this is not working. It's never been a problem before.
Yeah. So hi Mike, it's Dennis. So could you please go down, then you will see like a menu pops up. So yeah, there. So if you see like a cursor symbol on left, go left. Yeah,
yes,
please
I see
click
that.
on. Yeah, then probably you will continue.
Okay, let's try. Thanks very much.
Try. Yeah.
Okay, so the motivation for this work is on how spurious minima are created in a shallow neural network and how they can be annihilated by adding neurons, indeed rather few neurons. So where's this kind of coming from? Well, I will say a tiny bit about the theoretical computer science side here. As I guess everyone knows, most of the methods here in trying to get a general theory have involved fairly naturally limiting operations. The number of neurons goes to infinity, or the number of inputs goes to infinity. And one uses methods, say, from mathematical physics, statistical methods, or control theory. There's lots of different methods. But my understanding is that by and large, machine learning works incredibly well, but the theory suggests that it shouldn't. And so there's a bit of a problem there. At least this is my understanding from computer scientists. So this kind of work I'm talking about really is an attempt to address that by looking at, if you like, rather simple problems, but understanding them well. And the problems aren't just simple, but they actually do apply to general networks in various ways. So I do not understand what's wrong with this thing. Oh, okay, well, I've got to the next page. That's something. So basically what's underlying this is what's called a student-teacher model. I won't say much about that here. You all know the kind of picture. It's a basically 1.5 layer model. And if we take care of the outputs here, which are just shown as one output, then we get a typical 2-layer model. A little bit of notation I just need to cover, because there are some differences that are forced here because of the kind of context. So I'm going to let Wi denote the row I of parameter matrix. X in RD will be an input, and the output of the neuron I'll denote by sigma Wix, where sigma is the activation function. And there we go. Let me just say a few things here, because the notation's a little non-standard, especially for people coming from computer science. So the row of the parameter matrix is a dual vector. It's not actually a vector. And so when I write Wix, that's just a valuation. So I'm not using transposes here. There's a reason for this. And also I'm not using any vectorization because I'm going to be dealing at some point in a fairly minor way with representation theory. And it really makes a lot of difference there, being able to use matrices as opposed to just column vectors. Okay. Let's see, this is kind of interesting. Okay, so really the difficulty here lies with non-convex optimization. So just assume for the moment that we choose some fixed matrix in the D by D matrices. So I'm taking K, the number of neurons, to be D, and I refer to this as the target. Okay, and then I define the loss here in the standard way as an expectation over some probability distribution on the input space. And you can see the terms in there, they involve the activation. One is of the parameters evaluated at X, that's this lot here, and this is the target matrix evaluated at X, right? And clearly this vanishes if W equals V, because the two sums are the same there, right? Okay, right. And also we have LW is bigger than V. So this is giving you the global minimum, obviously W equals V. I think I'm having to, this is absolutely insane. Damn it. Okay, maybe I just used return. That seems to work today. Using gradient descent then, the kind of thing we want to do is to find the W that minimize L. So as I say, this is coming from a student-teacher network, but the idea is you're going to sample the initial weights from some distribution, maybe a normal distribution. You're going to run gradient descent. And then the question is, for almost all initial conditions, does the trajectory through the initial condition for gradient descent converge to V? Well, the answer here is no, trivially. And why is that? Well, obviously, if you look at the formula here for the global minimum, you can see that very quickly that the minimum value of 0 is attained when W equals V. I've already covered that. And it's attained at D factorial distinct values of W for generic choices of V. So in particular, if you look at the formulas here, you'll see that obviously you can permute the order in which the sum is taken. So any permutation of the first D integers will give you a reordering of the sum here, and therefore a reordering of the matrix, and you're still going to get 0 if that matrix W is V. So you have D factorial, basically, generically, distinct values of W will give you the global minimum. So this tells you this isn't convex optimization, right? In a way, just the symmetry here. And so more generally, you get the loss function here. Is that showing up on people's screens, that wretched thing? Yeah, okay, I need to keep my hands away from that. For the same reason, okay, you can permute the rows of W or the rows of V and you don't change the value. So this is actually an invariant function. Any row permutation of the matrix W here will give you the same value of the loss. Okay, that's a very quick summary through that. So for generic choices of V, the loss is an analytic function of W outside of a thin subset of the space of matrices, which is nice. So it means that we can talk about gradient descent. Actually, a lot more is true. That L is what's known as a sub-analytic function. I'm not going into any details there, but this is kind of slightly stronger than just analyticity on a thin subset of the, outside of a thin subset of the matrices. So what this means is the analyticity, or the smoothness, say, means you can do gradient descent, and the analyticity means you've got the possibility of doing some serious analysis on the problem. So let me point out that the loss is given by, I mean, this, I think everyone knows this for ReLU, the loss is given by this very geometric kernel. This is one of the things that really got me interested in this subject. This is a beautiful kernel here because it's so geometric. It just involves angles and norms, and angles and norms permeate the whole theory that I'm about to kind of briefly kind of summarize here. So this is one of a family of kernels, but it's the regularity that's particularly nice. Okay, well, there's a lot of bad news. So a local but not a global minimum of the loss is called spurious. And even in the simplest cases, the very, very simplest cases, there are a lot of spurious minima. This is one of the reasons why it's remarkable that things like deep learning work. So what can one say in general about the critical points and spurious minima in this problem when we carry out this kind of process of gradient descent? Well, the answer is easy here. At this level of generality, it seems very little apart from constructing pathological examples where everything fails badly. Even if you choose a very, very nice example for the target, it's still going to appear almost impossible to have kind of formulas, for example, for the critical points, let alone the loss and things like that. This is kind of looks pretty hard. So what do we want to do to cope with the bad news? Well, if we're going to do some serious analysis, it's really important to see how things change or don't change when we vary, say, the number of inputs. We'll vary the number of neurons in a little while. This is a kind of path-based approach. You want to deform, say, the number of inputs, increasing them by 1, 2, 3. But there's obviously a problem here. What can this mean in terms of the target as well? And this is really the focus of the talk, and it's much harder. What happens if we increase the number of neurons? So for anything we do to be worthwhile, the results need to be robust when we break the structure we assume to get the path-based approach. So what I'm saying here is, supposing I can prove some results about what happens when you add neurons, the spectrum of the Hessians here at spurious minima, I need to know that these results will persist when I break the assumptions I'm making that simplify the problem. And on that side, I can say they do. There's no problem with that here. Okay, so let's continue. So what I'm going to do here might seem a little bit absurd at first. I'm going to choose a very special target, which has a little bit of symmetry. So in this case, for the target, I'm taking k equals d here, just to start with. We take v to be the identity. And then if k is bigger than d, I'm going to regard v as the identity with k minus d rows of zeros appended to it. Okay, that's the first thing. Okay, and of course, I should have said that this v is naturally defined for all d. So this is already kind of solving the problem as to what happens with the target as I increase d. So it can be shown that with this choice of v, I'm not going to go through details here. This is really very easy. The loss function is invariant with respect to the action sk, which permutes rows, and the action sd, which permutes columns. Okay, that's the natural sk cross sd action on matrices. By the way, all this is true if we take v as an orthogonal matrix, any orthogonal matrix, but we won't get the path-based formalism if we do that. So how do we quantify symmetry here? Well, by what's known as the isotropy group. So in other words, we're looking at all the permutations that basically fix the solution that we hope we've got of the undergradient descent, the critical point. So a particular W, the isotropy group, the measure of its symmetry is the set of all row and column permutations which fix W. Okay. Now here's the first thing. The isotropy group of V is the diagonal matrix of SD acting on the D by D matrices. So this is just pairs GG. So first G will permute rows, the second G permutes columns. Okay, which is kind of nice. Okay, what we find interestingly is empirically, if you run gradient descent for k equals d or k bigger than or equal to d, spurious minima have isotropy conjugate to a large subgroup of this diagonal group. So that's kind of interesting. I don't know of any examples where you don't get that, by the way. So let's take a kind of question at this point, just to see kind of something that happens, is a Hessian spectrum of V at say k equals d, at least 4. Now, this isn't the sort of problem you set as an advanced calculus problem, for example, in your undergraduate advanced calculus class, because, you know, if we take k to be fairly small, say 100, the Hessian matrix has essentially 100 million entries to it. So this is potentially a really difficult problem. In this talk, I'll briefly show how we solve this problem, and not just for a rather simple Hessian spectrum computation like this one. So let me tell you what the Hessian spectrum is in this case, because it's rather interesting. There's an eigenvalue of quarter minus 1 on 2 pi, which has multiplicity d minus 1, d minus 2 on 2. There's another one, a quarter plus 1 on 2 pi, which has multiplicity d minus 3. So notice that here, this is d squared minus a linear term in d. So we've already captured most of the eigenvalues. And then the other two, there will be 3 eigenvalues, all which have multiplicity d minus 1, and then 2 with multiplicity 1. The O d minus 1s aren't serious here. These all come from solving a quadratic equation, and they're just approximations. Okay. Interesting thing here is already that if you look at a Hessian spectra for spurious minima in this problem, which I'll get to in a minute, it turns out that these numbers here are characteristic of what you see. You get these eigenvalues in particular, which are very large when d is large. You notice there's one there of multiplicity d minus 1. There's a growth of d plus 1 on 4. The other one is d on 2 pi. So this spectrum you see here is already typical of spectra that you get for spurious minima. And this kind of is compatible with conjectures on a curvature of landscape geometry at spurious minima. There seems to be some kind of self-similarity operating here. So the question is, when we come to the question of creation and annihilation of spurious minima, creation is the thing to think of here. Which of these eigenvalues are important? Because we're going to be changing the sign of an eigenvalue. So it turns out, just the Hessian spectrum at V I'm talking about at the moment, that it's this one that's important, the one in red. That's the one that plays the role, and it also plays a vital role in the annihilation of spurious minima. So these little eigenvalues here are associated to what's known as the standard irreducible representation of the symmetric group on Rd minus 1. That's the action induced by permutation of coordinates. So this is a kind of pretty standard object, and it's fairly simple, unlike the representations that are underlying these things. Okay. Okay, so let's now look at the families a little more carefully in fixed point spaces, just to give you an idea of how the path-based methods come in. So when k is d, you've got 2 families of critical points here, which have isotropy smaller than that of V, which is the critical point giving the global minimum. And these give spurious minima. I'm only going to discuss one here, and it's the one that's seen under what's known as Xavier initialization. Xavier initialization is used in learning, statistical learning, it's a way of avoiding blowing up of the algorithm, or alternatively kind of bad coordination between layers. I won't go into details here. I'm only going to talk about one of these things. So I have to say what the fixed point space is. That's the action of this group, the diagonal group on the matrices. And here, the dimension I can give, it doesn't depend on D, that's vital. And grad restricts to a family of vector fields on this space, the fixed point space, which is defined for all real values of D bigger than 3. Okay, so let me give an example because it might seem a little bit opaque. This is a matrix from MD plus 1D, which has this symmetry. So if you look at this matrix here, focus on the first D minus 1 columns and go down the first D minus 1 rows, and you have this matrix here. You'll notice it's diagonal. All the A's are diagonal entries are equal, and all the off diagonals are equal. This is the part that is coming from the symmetry SD minus 1. And you'll notice here, just let me show you this, just focus on a transposition where you interchange row 1 and 2, and you also have to interchange column 1 and 2 here. So if you interchange row 1 and 2, A goes to A, and then you intertrace the columns, and then this A will go back here. So that simple 1-2 transposition flips the A's and flips the B's, and that's why all the entries in there that are equal. And then you have some other things, these rows here where all the first D minus 1 entries are the same, and so on. This comes from, again, the SD minus 1 action on the columns, from similarly over here. So that's what the kind of matrix looks like for this problem at this point. Okay, so first bit of analysis here is that when you look at these critical points, and generally all the critical points that are seen in this problem, you actually have a representation of the critical point in terms of a fractional par series and 1 on square root of D. So like this is on the fixed point space. I've identified it with Rn. So you get this par series in D to the minus 1/2, and you can compute these coefficients. I'll give you an example in a minute. And if you can't compute them, which sometimes you can't when K is bigger than D, well, you can't give a formula for them, you can compute them using Newton-Raphson, okay? So the other thing is this is in D minus 1/2, but D minus 1/4 is also possible, and there are other possibilities too. So at this point, what we've got is some tools. We've got fractional par series representations of the critical points, representation theory, which gives you these high multiplicities, and I haven't used this yet, some things coming from bifurcation theory, which gives you precise and explicit estimates of the Hessian spectrum, decay of the loss, and much more. So let me just show you the sort of formulas you get here. So let's look at the dependence of the loss on K minus D for this family I'm talking about. So what you find is the loss looks like constant times D minus 1 plus terms in 1 over D to the 3 on 2. So here, the first one is actually explicit. That's when K equals D, and it's 1/2 minus 1, 2 on pi squared. The others you have to compute. It's actually decreasing here. So this is the sort of spurious minima that comes up in practice. It's not as bad as it might be because of the decay rate of the loss. So even though it's not giving you the global minimum, when D is large, it's giving you pretty close to the global minimum. So let's look at the other families I haven't really talked about. I think I have to have one formula of a sort in the notes. So this is actually the fractional par series, the first few terms of it anyway, for the case where you've added 1 neuron to the problem. And you can see that you have rather explicit terms here, which actually involve quarter pars of D, not just half pars. The loss, which keeps getting hidden by this little thing at the bottom, let me just show you that. When it goes away. Okay, it's frustrating, this thing. So what you see here, the loss does not decay to 0. It's 1/2 minus 1 on pi plus a term over root D plus then a term over D to the 3/4. So this loss doesn't go to 0. So this would be a bad kind of spurious minima to occur in the learning process, because the loss is not going to 0 as you increase the number of inputs here. And this is one of the reasons Xavier initialization does not pick this up, which is good. Okay, so assume then the family of critical points I'm looking at, then this is a hyperbolic saddles if d is less than or equal to 5, and spurious minima of d is greater than or equal to 6. This is easy to check. We're talking small values of d here. So at somewhere between 5 and 6, this becomes a family of spurious minima. So using the analysis coming from this fractional power series representation, we find that Hessian spectrum is defined. It's got an FPS expansion for d greater than or equal to 3, and the change in stability occurs at approximately d equals 5.58. This is associated to a change in sign of one of the eigenvalues corresponding to this standard representation of SD minus 1. So in this case, we're looking at the representation of SD minus 1 on this space of matrices here. It actually has 5 copies of the standard representation. And as you go from D5 to 6, well, at D less than or equal to 5, one of the eigenvalues is negative, and they're all positive when D is greater than or equal to 6. Okay, let me back off that a second. I don't want to go there for a minute. I can't go back, I won't. Okay, so let me just say a little bit about this. I'm getting this strange number of approximately 5.58 because I can restrict everything to the fixed point space and do the analysis there. And there the spectrum has a fractional power series representation. Everything depends nicely on D. Think of it as a real parameter, the determinant of the Hessian, the eigenvalues of the Hessian. And we can also increase the size of the fixed point space to check that in fact all the changes in eigenvalues or changes in spectrum do occur at the same kind of point. This is something I'll explain a bit more later. So this brings me to bifurcation on the standard representation. This is where the dynamical bit comes in. So this is kind of known for a long time. The original work was done by Roger Richardson and myself about 30 or so years ago, actually around about the time that deep learning and backpropagation and these sort of things were taking off, but I knew nothing about that at the time, and we never thought that this might have some connection. So I'm going to just tell you a little bit about this, and this is the kind of thing I think in this talk is the most interesting part, really. So we look at the standard representation on Rn. It's very geometric. I'll show you in a minute. We're going to take n plus 1 odd. It makes life simpler. So, and I'm using n plus 1 here. Notice this is a little switch, but it just makes the notation easier. So I'm not using d's here, I'm using n's. So n is 2l, l is half of n, right? And Sn plus 1 acts on R2l. By the way, index here counts the number of negative eigenvalues of the linearization of a vector field at 0. It's always a little bit confusing here because when you look at the gradient and critical points and minima, the signs you're using are opposite to those of gradient descent. So I'll try not even to get tangled up in that.
Yeah, so Mike, just 5 minutes, yeah?
Okay, well, I'll see how I can do. I will stop in 5 minutes. I want breakfast. The origin is always a 0 of a Sn equivariant vector field. Okay, that's the first thing. So generic bifurcation for this is actually a little complicated. Going from a source on R2L at the origin to a sink or a sink to a source, what happens is you get a simultaneous collision of 2 to the 2L minus 1 saddles of high index. So I'm going from a sink to a source here with the origin, followed by the emergence of 2 to the 2L minus 1 saddles of low index. All these saddles actually lie on axes of symmetry, and I'll do that in a second. The high index of pre-bifurcation saddles has a very interesting implication. It means that when you're close to the bifurcation point, trajectories from afar approaching the origin will tend to be trapped by these saddles of high index and then sent back out again. So you won't see many points actually going to this minimum point at the origin. And this is exactly the sort of thing that happens when you start increasing D. Spurious minima at first are very infrequent, and then they become very frequent. It's a kind of mechanism like this that's involved. So let me give a geometric example that's not quite to be taken too seriously. So I'm drawing a tetrahedron here. These symmetric groups are naturally associated to high dimensional tetrahedra. So let's look at the tetrahedron in R3, understand that we should be looking at the tetrahedron or in R4 because I'm excluding R3 and R1, they're the odd dimensional cases. But anyway, this has two axes of symmetry, two types of axes. There's one joining vertices to midpoints of faces. There's four axes here. When the isotropy is conjugate to S3, this is just, I should have said the tetrahedron naturally permutes S4 naturally permutes the vertices of the tetrahedron. There's four of them, gives you S4, and that gives you the action on the tetrahedron. And similarly, we have three axes joining midpoints of opposite sides, and these have isotropy conjugate to S2 cross S2. Okay, now you need to go up a dimension to get a valid model. But what happens is, in the case that I'm interested in, is that your saddles will come along here and they'll all meet at the origin at the same time, and then they pass out the other side. And that's the symmetric bifurcation. So what happens when we break the Sn+1 symmetry here? Or, thinking of the original model, the symmetry of the target, the center manifold reduction, right? But that's the way we'd kind of look at this. So what happens? Well, outside of a neighborhood of the bifurcation, nothing much will change. What was a hyperbolic saddle point before will still be hyperbolic, right? So I'm interested in what happens near the origin. Well, this can be very, very complicated, not surprisingly, but there's a minimal model of the complexity. So I'm talking about forced symmetry breaking here, and I just want to describe that. So it consists of a stable symmetry breaking perturbation. So where we forget about the symmetry here, with a minimum number of saddle node bifurcations and the maximum number of crossing curves. Now let me explain that. So here's a kind of picture. So before I break symmetry, everything, all the saddle points on the axes went through the origin out the other side, and they all met at the same time. When I perturb and break the symmetry, what will happen is some curves will cross. These will all be of index L, and there'll be hyperbolic saddles, and other curves will join like this. So for example, the original sink, say, of index 2L will meet up with the curve of index 2L minus 1 along an axis, and they kind of annihilate each other, so that disappears. So in this region, there's not many critical points left. So that's a kind of brief model. That's a crossing curve, which is a nice curve, which is kind of hyperbolic the whole way. Other things get annihilated. There's a period where there's in the middle where there's nothing really corresponding to that original sink or source. So let's go over. Change in index is always plus or minus 1. So what happens is there's a minimal model of complexity here. So in other words, the way you should think of this bifurcation of the symmetric group on the standard representation, the bifurcation, is that it's a kind of encoding a lot of complexity. It's encoding how, in fact, things like saddle points become spurious minima in neural networks. So the upshot is you have the minimal model, which has exactly this number of crossing curves and exactly this number of saddle node bifurcations. Every stable family has at most that number of crossing curves and at least that number of saddle node bifurcations, right? So this is kind of estimating the complexity. And you have a similar result, a little more difficult, when n+1 is even. So let me give you an idea what this is saying. Suppose, for the sake of argument, we take n+1 is 17. Then the middle model here, this is the simplest kind of model for symmetry breaking, will have 52,666 saddle node bifurcations and 12,870 crossing curves of index 8. Okay, but what does this mean? We'll go back to the geometry here. We're looking at the loss function. We want to look at the landscape geometry. We have a saddle point, a hyperbolic saddle point of, in this, through a center manifold reduction that is going to change into a minimum, right? So a spurious minimum. So what we want to do is to form the landscape near that point in such a way that we don't introduce more than one minima at any point. And this is exactly what this is doing. It's a purely local bifurcation. There's nothing coming from outside. We're not creating any new minima through this process. It's purely local, and it's very unusual, by the way, in bifurcation theory, equivariant bifurcation theory. Okay, I'm going to be stopped in a minute, I know. So I'm almost finished, actually. So here's what I'm not talking about, because it would just take too long. But this is really answering starting to answer some kind of significant problems in the theoretical work. So adding one neuron annihilates spurious minima which have the maximum isotropy, that's delta SD, and they exist. Adding two additional neurons annihilates all the spurious minima with isotropy SD minus 1 through mechanisms very similar to what I've just been describing, really, in terms of the standard representation. And no new spurious minima. This is the important thing, and created when we do this. So we add neurons and we kind of annihilate the old ones. Actually, it's not quite true. We create what I call fossilized sets, which are kind of records of the old spurious minima, but they're no longer spurious minima. They're just kind of degenerate and they don't attract trajectories. So it's possible that just adding two neurons for this problem annihilates all the spurious minima. Okay. So similar to what happens for delta SD minus 1, the annihilation depends on the creation of descent directions in the isotypic components corresponding to the representation. I can't possibly go into that here. Concluding comments, I'm almost there. Minimal model hints at the complexity of the changes in landscape geometry that are involved in the creation and annihilation of these spurious minima. It's a kind of indication why not much progress has been made on this. This is really hard. I mean, what's going on in the geometry? The symmetric model is robust in the sense that creation and annihilation typically occur at non-integer values of D. So if we fix D, we can perturb and we have results that hold on a non-empty open set of families of targets, for example. Okay. Now, okay, you're going to say, oh, this is very special, right? Fair enough. Generalization beyond robustness to force symmetry breaking, almost certainly yes, even for the fractional path series results. Statistical techniques, though, will play a significant role. I obviously am not going to say any more. So thanks very much for your attention. And I suggest it's time for lunch or breakfast now. Thanks very much.